So when we're dealing with the osmosis lab, the write-up that I'm going to expect from you guys is something that looks like this, where, again, looking at kind of the expectation of a scientist, when a scientist does something, often students think of Bill Nye the Science Guy, where there's all these great little activities that, they demonstrate phenomenon that scientists study, and that's great. But half of science is recording the data and making sense of the data. You have to be able to make a statement that can be tested. You have to be able to argue based in facts and not conjecture or supposition or feelings. So, following the scientific method, you have to start with a question. And the question is, how will the system behave when placed in different environments? What are the three different environments that we place a system in?
It was water in the beaker, water in the other beaker, and then water with 10% sucrose in the beaker.
Very good. Water, and 10% sucrose. The conditions, though, ultimately, we know the words, the terms that we would use for them. We would say hypotonic, isotonic, and hypertonic. But yes, you're right. Those are the three conditions. Then the hypothesis is that water will move, and I don't know what happened to the words I had written there, but they disappeared. Water, oh, I see. I see it. Let me, for some reason, it got jumbled up there. Water moves toward the hypertonic solution when the solute cannot move. What do we call that when water is moving?
Diffusion.
Osmosis. Or the diffusion, which is the diffusion of water. Which again is why this is a passive process. No extra energy required. And anytime someone asks you, is energy required, they're asking you, is any extra energy required? When we look, of course, you want to write down the materials you used. In a good science, and if you're doing a real write-up for a journal, let's say you're trying to get something published, you would actually write down exactly everything you use. What kind of triple beam balance? You would write down your procedures. You'd explain how you cut the dialysis bag. You would control the length of the dialysis bag. You would write down what kind of dialysis bag you used, right? The brand name. Why is that important? Can anybody think of why it would be important to write down the brand name of the dialysis bag? Yeah.
Because different dialysis bag can be made different by different people.
That's right. And so how might that affect your results? Yeah.
I was saying, and if somebody wanted to keep going on with the experiment, they needed to know everything that you did with it.
Perfect. That's absolutely right. Absolutely right. They have to be reproducible. Your experiment has to be reproducible. And you're right as well. Again, trying not to use names, right? You're right as well. It's very important that we know what kind of dialysis bag, because what if there's something wrong at the manufacturer end? What if we find out later after we try to publish, somebody says, hey, wait a minute, those dialysis bags actually let sucrose through. Oops. So it's important that you write all this information down so that later when you're in your own notebook, if you were a scientist doing your own work, even without publicizing it, you would want to make sure you record all this information. So when you go back and you're looking at your results, which we're all going to look at in just a second, when we look at these results, we're going to say, hey, wait a minute. How did we get these results? And are these results reliable? And can they be reproduced? Are they reproducible? All right, so we use a triple beam balance, three dialysis bags, which is from a roll, the same roll, right, that we cut up. Notebook paper, 10% sucrose solution, and string, right? Those are the things we used. Yeah.
Wouldn't water go under materials too?
Wouldn't water what?
Wouldn't water go under materials too? If you did.
Okay, yeah, I think it's a good point. It's a valid point. Water, and it's tap water, right? We didn't use distilled water. Why didn't it matter? There are ions in tap water, right? Distilled water is purified water, water that has less dissolved solids. But this water had dissolved solids. Why did we not worry about it when we looked at this experiment? Why would someone say, hey, wait a minute, how do you know that this dissolved calcium and iron and salt in the water, although I grant you it's only a small amount, why is it not, how do you know it's not impacting your results? Yeah.
Maybe because it won't move through the dialysis bag.
Okay, it might be because it's not moving the dialysis bag, but wouldn't that make osmosis? Wouldn't that make osmosis move then? What is it that makes it so we don't have to worry about it? How do we get rid of it from our concerns?
Purify the water.
Well, did we purify the water?
No.
No, so could that impact our results? I'll tell you right now, it wouldn't likely impact our results. Why though? Look at this setup and explain to me why I'm not worried that we just use tap water instead of distilled water. Yeah.
Well, you said something a small amount.
Okay, so that could be that's a valid statement. There's only a small amount, so maybe we think it's insignificant. But there's actually a much more fundamental reason why we're not worried about it. Yeah.
Because you use that same water already.
Exactly. We use the water, everything, the same tap water was used for everything. There's tap water here, there's tap water in the 10%, 90% of this 10% sucrose solution is tap water. There's tap water everywhere. So if the ions in the tap water were gonna make water move, what would happen here?
It would like
Water would move, right? So the fact that we have tap water as a control group, see tap water, water, and the control group is the isotonic solution, right? We're able to compare the movement of water to this isotonic group, which is what makes it our control group, right? Our negative control. We expect nothing to move, no change in our mass here in this group. Yeah.
So it would have been different if you put distilled water in one and then tap water in
Oh yeah, that might make a big difference, right? And I'm not sure if I know how it would change it, but you'd have to. That might be a question on an exam coming up in maybe your final in the semester. How would distilled water change this experiment? Would it change this experiment? Yeah.
Do you think distilled water, due to it being purified, would cause the water to be able to move quicker without having to go through all the different minerals that are still inside tap water?
Move quicker. Who remembers the extra credit assignment that I gave you, which I'll give you the questions tomorrow? The water potential changes. Right? Remember that water potential? Go back and read your documentation on water potential. And tomorrow, what are the three things that tell us how quickly osmosis happens? Yeah.
Pressure and temperature for the
That's right. So go back and look at it. That's right. Pressure, or what we call water potential, right? The pressure potential. Remember that? Pressure potential, water potential. Go back and look at the three things in general, what makes things move. So if we would have used distilled water, then our water potential would be higher, wouldn't it? It'd be less negative. But because this is tap water, our water potential is more negative. How does that impact osmosis? You can look at that formula, right? That tomorrow you'll get some extra credit questions, exam questions tomorrow for bell work, okay? All right, controlled variables. What did we control? What did we keep the same? The water, the tap water was the same across the board. Dialysis bags were the same. It was same dialysis bag, same roll of dialysis bag, not just the same brand. The 10% sucrose solution was made the same way. All of it was from the same sample. Yeah.
Could you consider the triple beam balance a control variable too?
Yeah, you could if you use the same triple beam balance throughout. My concern with putting that as a control variable is that you could have used the triple beam balance to measure the pre-weight, the pre-mass, and maybe you came after lunch, you used another triple beam balance. Did you use the same one?
I think I did.
You'd think you did, but we're not sure, right? And so that's what a scientist would say, okay, well, maybe we don't put that in a control variable, because we did use a triple beam balance, we used the same procedure, but changing the triple beam balance might have made a difference, so let's not put that as a controlled variable. So we didn't really control that variable. We weren't sure what was going on there. So control group, now I don't think it mattered as long as your procedures were consistent and correct. Because there is what we call experimental error, right? We're going to talk about sources of error in just a minute, okay? But when we're looking at controlling variables, we want to control as many of these as we can so that we can be able to reproduce it, to be able to identify any serious issues that might have arisen in the experimental design, anything that was surprising could have been due to error, or maybe we proved something, maybe we discovered something. We can't tell if we don't have controlled variables. So of course our control group is this isotonic solution, because what is our hypothesis is that water is going to move towards a hypertonic solution. So therefore, where there's no hypertonic solution, we expect nothing to change, no water to move. Right? So that's why this is our control group. Isotonic would be our control group. All right, so that was pretty cool, right? That was an experimental design, scientific method. We did it. I'm going to go ahead and kind of shrink all this up if that's okay. Everybody have it? Should have had plenty of time to get that done there. So now let's look at the data. Look at the data we collected. And we had, how would we organize this the best way? I guess we can go ahead and look at which beakers we have, just like we did before. The bag, and we'll call this the trial. Now the trial is going to be done by different people, right? Different groups. I think we had like 4 or 5 groups here. By the end of the day, when I post this video at the end of the day, what'll be interesting is I'll have the entire 9th grade's results, right? So everybody here should be able to give me result data, right? Is that correct? All right, so we have bags, beaker, and then we have mass before, mass in grams before what?
Before you put it in the solution.
And after, right? And by the way, as part of our procedure, it's always good to describe what we do, right? And, you know what else was controlled? The temperature. It was all done under the same conditions, right? The temperature and the pressure was all the same. We didn't do one on top of a mountain and one at the bottom of the ocean, right? We did them all at the same temperature, same pressure. So we call STP, standard temperature and pressure. Because in Cleveland, we're actually at 1 atmospheric pressure, so we did everything in STP. All right. Trying to get this so it lines right. Okay, so let's start collecting this data then. Oh, wait, we want to talk about our mass. When we did our masses, when we looked at our masses, the way we calculated this was what? We measured the mass of what? the weigh boat,
And then subtract it
then plus, all right, we had that down, we wrote that down. Then we added the bag. Is that correct? Finally, hold on a second. We subtracted the weigh boat. In grams. Is that right? So we took the weigh boat, I'm going to put weigh boat, WB, not the network. WB minus bag mass equals bag. Do you agree? So that's what we did. We took the weigh boat. Ooh, not the weigh boat. That's not right. Everybody agreed. No, I was wrong.
Nope.
We took the weigh boat plus the bag and subtracted, right? We had those two. Subtracted the weigh boat mass, and that equaled what? The bag mass in grams. Everybody okay with that? Now that's right. Question? All right, so let's go ahead and get and write down our various, do trial 1. There's probably going to get at least 6 trials here. Our first one, let's look at when the bag had 10% sucrose. And our beaker had water. When you had a trial 1, an experiment 1, we had sucrose. Experimental group 1, we had 10% sucrose. We had water in a beaker. Who wants to be the first trial people? Trial 1. All right, go ahead. What was your, yeah?
Me?
Yeah.
Okay, before we had 5.6 grams. And then after we had 7.9.
All right, any more for trial 1? Again, this is 1, or rather group 1. Let's see, I should put this group 1. Group 1, trial 1. Trial 1 is gave us 5.6, 7.9. Anybody else with this same group? Yeah. Same group, not same group of people, but the same test group. In other words, 10% sucrose, and the beakers had water in it. Somebody else give me some data for trial 2. Yeah.
We had 2 grams in our bag for the 10% sucrose. We had 2 grams beforehand, and the aftermath was 4.5 grams.
Of course, here's the same, and this is the same. Trial 3, third set of people, third set of data on the same. I should have at least 4. I cut up. Where is everybody else's data? Yeah, go ahead. Go.
We had before we had 2 grams, and after we had 4 grams.
All right. Yes.
Before we had 9 grams, and after we had 13.
Anybody else? Is that it? We only have 4 groups. Yeah.
How can we measure? Why do we need to use the weigh boat?
Yeah, that's really a good question. Why use the weigh boat at all? Why not just put it directly on the balance? You could do that. It's best to use a weigh boat because it protects the balance. It's best to use the weigh boat because if you had it's good experimental design. You don't damage. You see it. Who saw the little rusty stuff on the balance? That's from people putting chemicals directly on the metal. It shouldn't happen, right? You should use a Whiteboard. So it protects the balance, but the other thing it does is it allows you to move things around. Does that make sense? So you could pick up your your bag without messing up the balance settings. Does that make sense?
Yeah.
And you can move things around without having to mess it up. Also, I think that about does it. Also, if you had like a powder, it wasn't in a bag, you could take the Whiteboard and pour it out and pour new powder in. And lastly, who saw the liquid that was that came off the bag? Because you're pulling it out of a beaker full of liquid. If you put it right on the balance, that water's going to stay on that balance, won't it? So next person that uses it, the amount of water on the outside of the bag is going to start to add up. So imagine doing that all day with the same balance. You could end up with a nice little 3 or 4 gram difference in mass simply because you have water on the balance. Does that make sense?
Yep.
Yeah.
Also, like, for this case, didn't you say, like, the sucrose is sticky, and, like, if we put on, like, the balance, like...
That's right. The sucrose is sticky, so that could also add to the mass. So even if the water evaporated between now and 4th period, right, the next period that's going to use that balance, that they won't even know. It's clear, so they won't even know that there's sugar on that balance. But they're just putting it right on there, and that could impact their mass. So it's a very, very good points here. So these are all issues of good experimental procedures. Yeah.
Isn't all of those trial one and they're different groups?
Yeah, okay, that's a good question. So when I say groups, we're saying experimental group.
Oh,
Do we have to write all the different groups, or can we just put our results?
I would put all of them in the table that I'm doing, and then I would mark which one was mine. So if I was group 1, I would say, okay, I would make a little asterisk, a little green asterisk or something right here. This is my group. So every time I look at the data, I know my group was always trial 1. All right, are we ready to go on that? It's everybody, right? Everybody's data that did it is here, 1st period. Is that correct?
Yep.
All right. And we'll add these together throughout the day. You'll see we'll have a lot of data. Do you see the differences, by the way, in the different people that did it? You see we all had, these two interestingly had the same mass before, and about the same mass after, minus 0.5. A couple concerns and things you need to be thinking about, because we're going to get into a discussion about error in just a second. What about this difference? We both started with 2, but why? Think about our experimental design, what we actually did in the experiment. Why was there a 0.5 difference in mass here? And is that acceptable? So we have to think about, is that error acceptable? So we have to think about that. Here's it. What is it that you notice? What part of this data supports our hypothesis? Yeah.
the aftermath is bigger than the before mass.
The aftermass is in all situations are bigger than the before masses. It's the question that you might start thinking is, why is the increase not all the same? Why, especially you can see there's a difference here with the beginning masses are the same. What was the difference? And so just think on that. Yeah. Could be time. Excellent. Excellent. Good thinking. That's right. Time could impact how water moves, because the longer it's in the water, then maybe the more water that moves. It has more time to equilibrate. Very good. Because we didn't control time, did we? So if we were going to redesign this to try to get this to be all the same differences, can get this as tight a set of data as we could get, to get it as accurate as we could, maybe we measure the same amount of time. We keep the same 20 minutes. Because I can tell you from experience, some people did it right here in class. Some people came here during advisory to get their data. So some people waited a whole 2 hours almost before they got their data. Some people did it in the 20 minutes. So that could easily explain some of this. All right. but there's some other considerations. See, that's great. That's fantastic. Now that hopefully that shows you why we have to control those variables, right? We have to try to keep all those variables the same so when we collect data we can compare it. All right, so group 2, experimental group 2, which is where, and we're going to go for trial 1 again, and in this case where we have water in the bag and then water in the beaker, right? Who was experimental? Who was trial 1? Go ahead.
We had 3.6 grams before,
3.6.
and then 3.6 grams.
3.6. So that's pretty neat. I'm glad to hear that. Why is that good news? Please don't go changing your data, because I'm telling you, I don't expect it to be exactly the same across the board. That would worry me if that happened, right? I expect there to be error, and so everybody needs to never ever change your results in an experiment. It's the worst crime you can do in science. To change the results in order to fit your theory is the worst crime we can do in science. All right, so I just wanted to correct this because I wrote weaker for some reason instead of water. Because I was saying beaker and writing water and it came out weaker. So whatever. All right, trial 2. Again, water and water. What do we got?
We got 3 grams and then another 3 grams after.
Nice. All right. So it sounds like people are doing some. Well, I hope. 3. Yeah.
We had
6
6 before and 6 after.
before and 6 after. Wow, you're doing pretty good here. And the last group 4. Yeah.
We had 2.5 and the same thing after.
Couldn't ask for better results there. What this tells me, this control group. Remember, this is our control group, isn't it? We expected these results. These were expected that they would stay the same. So that's excellent. But what also this helps me understand is, are people using balances correctly, right? Because if they weren't using it correctly, there would be a difference in these two. I expected, honestly, to see a little bit of a difference between the masses. But either one of two things is happening. Either the airs kind of nullified each other, or people are really doing an excellent job in measuring their masses. So, in any case, trial 3. I'm sorry, group 3, experimental group 3 rather. Trial 3, or trial 1. Go.
6.2 grams before.
So in the bag you had water, right? And
Beaker 10%.
10% sucrose here. And then you had, what was it?
6.2 before and then 4.5 after.
Wow. Drastic difference, man. Did you notice the size difference, by the way, guys, when we were doing this? Did we see a difference in size? Did we see swelling? Did we see shrinking?
Yeah, the lab was all printed.
All right, so trial 2,
We went from 9.0 to 5.0.
9.0 to 5.0. And trial 3,
We went from
what was it?
We went from 3 grams to 2 grams.
3 grams to 2 grams. Excellent. And the fourth group,
We went from 6 to 5.
6.0 to 5.0. Notice how I'm putting these .0s. You see that?
Yeah, why do you do that?
We're doing that because there's something called significant digits. We're going to talk about that as well today. Significant digits. So there's 2 things I want to add on to our discussion about the scientific method, and that's error. I want to look at error. Experimental design error, experimenter error or measurement error. And I also want to look at this idea of significant digits. So So excellent data. This is from first period. Did anybody take pictures? Yeah, could you guys email those pictures to me so I can include them in the video later? All right. So you guys happy? Isn't it wonderful when things work out well? I mean, I really, sometimes science works. And we learn something every time, whether it works the way we think it's going to work or it doesn't. Either way, it gives us information. It gives us information about what we're doing wrong, and in fact, when science doesn't work and we're not doing anything wrong, that's the most exciting time, because we've just discovered something new, right? When people looked at the retrograde movement of Mercury and Newton's equations didn't predict it, right? Couldn't explain it, and Einstein's could. That was exciting. When Einstein predicted black holes, never seen one. And then all of a sudden we start to collect evidence of black holes. It's pretty exciting, right? Yeah.
Aren't there, I forgot what they're called. They're like called something bare, but they're able to withstand black holes in the vacuum of space. But it's,
I don't know about withstanding black holes. I don't think anyone's ever, to my knowledge, done anything even gotten near a black hole. We've only seen the impact of black holes on light, for instance, or other objects. So we can see how the movement of celestial bodies and light itself acts around black holes, and we can see that through a telescope. So that's the evidence that we've collected over time about black holes. Does that make sense? We can't even see a black hole because it's black against a black background, so we don't see it, right? However, we see light bending around it. We see a planet should move here, but all of a sudden it moves kind of wobbly around this particular area. That tells us that something really massive is changing the movement of a planet. You know, that's a big deal. So that's how we know about black holes. I believe what you're talking about is tardigrades. They're called water bearers.
yes.
Yeah, those are you can dehydrate them. They can withstand the vacuum of space, which I think is what you're speaking of when you're saying space. They're microscopic little organisms. They have tiny little legs. My wife gets freaked out when she sees them. I love to discuss them there. I think they're cute, but she thinks they look like little monsters. Yeah, the tiny little legs. They got little chubby little legs. Like they look like pugs.
You want to know?
And they got little tiny little. But you're talking about a guy that loves insects, and I love all life. I love fungus. I love taking care of pictures of fungus. I have some great pictures I'd like to share with you at some point. So.
Yay, pictures.
And slideshow, family vacay. All right. So anyway, so when we're looking at the data from this experiment, that really does support our hypothesis, doesn't it? So in our analysis now, we're going to do something called chi-square. We're going to analyze how. Yeah, it's chi-square. It's a crazy name, and every time somebody hears chi-square, they constantly think of squaring something. You guys did squaring, didn't you? Yeah. In math? All right. So everybody always wants to do, when they see chi-square, they want to talk about squaring something. And it's actually not, it doesn't really have a lot to do with squaring something. So it's an unfortunate name. Let me pause this. So the video I want to show you on chi-square is going to be from Khan Academy. It's about 10 minutes long. Maybe 11 minutes. I think 11 minutes is it. And chi-square is about goodness of fit. So when we look at this data, we're looking at this, and we ask ourselves, wait a minute, is this good? Does it fit our hypothesis? Okay, it does. So we're good, right? We can go on. We can publish. We can say, yeah,
No.
we did a great job.
No.
What someone's going to say is, wait a minute, how do you know? How do you know that there's not an error that just happens to fit your way? You know, sometimes the errors, you ever get an answer right on an exam for the wrong reason?
Yes.
Happens all the time, right? Oh, I was right. Wait a minute. That's not what I thought it was. I thought it was because of this. So when we have data, we have to try to see how well does it fit in an objective way. And Khan does a good job of it. I'll put the link for it in the video when I post this video. Yeah.
During the beginning of the year when we were talking about like nothing is, we're not 100% sure about anything. Is that why?
Excellent. Yeah, that's right. We're never in science 100% sure about anything. And so what we do is we give ourselves some plus or minus. I'm pretty sure about this. It's possible something else is going on. You know, maybe the planet is flat and we're riding around the sun on the back of a giant space turtle. That could be happening.
Space turtle.
But the evidence is clear that it's not. So I'm going to go with it. It's not. And so in science, we have to go with what's our best possible solution. It's called.
Like an inference.
Yeah, we're making inferences all the time. That's what analysis allows us to do, is to make an inference based on the facts, right? But what we do is we do Occam's razor. We apply Occam's razor, and you'll know more about Occam when we do cladistics and some other conceptual stuff. But Occam was a mathematician. And he said, look, I'm paraphrasing, okay? So I'm going to say, he sat back and he said, the right answer is probably the simplest answer. In almost every situation, look at all your possibilities and ask yourself, what's the simplest answer? Go with that one first, right? So you see a light in the night sky. And it's moving around in an odd way. Maybe you hear some weird noise. And so what could be the answers there, right? So could it be aliens
Yes.
probing your neighbor and returning their unconscious body to their bed without them knowing, in order to do experiments on humans and possibly evolve the human race towards some alien designed plan?
My neighbors really mean
It's possible,
My neighbor's real mean.
right? And you could sit and imagine a million possibilities, right? Could that night light be a demon that escaped hell that now is trying to, it's Halloween, so I said let's have some fun with it. Could it be a demon that just somehow escaped hell, is now attacking your neighbor because, I don't know, that your neighbor's mean. And so now he's made a deal with the devil, and the devil's come to collect his bounty. It's possible. Sure, okay, all right. But in science, it's like, okay, what is the simplest, most reasonable answer that requires the least amount of variables to be different from what we expect? Right? What's the least, and that's where, you know what I'm saying, yeah? Okay. So Occam said, look, just pick the simplest answer and test that and go with that until you get other evidence that says that can't be, right? And so you see that light moving around. It's probably some kid playing with their flashlight or their drone in the middle of the night. That's probably what's happening, right? So, as I said, you're just looking at, oh, it's a drone, and you go to bed, and it turns out to be an alien. Oh well, you're wrong. But the question is not. Remember, in science, it's not like we say, oh, we're sure. I know it's not an alien. No, what we say is, look, it's highly unlikely that that's anything but some kind of drone. And I go, it is all the other possibilities, unless I find evidence, right, that it's not. If I walk my happy butt over there and I see a space saucer land and little blue guys come out of the thing,
There will be green.
oh, it could be anything. Are you green if you rather? Some little green guy come out. I would argue blue is probably a higher probability because of cyanide's ability to capture oxygen. But anyways, so anyways, here's this alien coming out of the thing. It says, you know, Boogadooga, how you doing? At that point, I'm kind of like, okay, well, I'm thinking it's my brother setting up some elaborate joke at that point. But given enough clarity of detail and assuming I'm not high, I'm going to go ahead, which I don't get high, so that's probably not the case. It's likely it's an alien. So I'll have to go with that. So do you see the number of things that had to fall into place in order for me to accept that this was an alien, right? I mean, I had to actually be there, collect data, and see. I mean, the number of possibilities starting to get. It's what did Spock? Well, someone once said. Spock in Star Trek said, he quoted someone else. I can't remember who actually originally said it. It's a famous writer, but he said.
Sherlock Holmes a lot.
And I think it was Sherlock Holmes. That's right. So Sir Arthur Conan Doyle, who probably quoted someone else, but
Who quoted Spock?
yeah, it would be nice if Arthur Conan Doyle. No, it couldn't have happened.
Yeah, because
Sherlock Holmes might have quoted Spock.
yeah, Sherlock Holmes quoted Spock on the show Sherlock, and when the same actor was playing Khan in the Star Trek movie, he got the back of playing Spock to quote Sherlock, so it would be a double parallel.
Nice. But that was a movie thing. My point is Sir Arthur Conan Doyle, the original writer of Sherlock, died a long time ago. So, anyways, what he said, what Sherlock Holmes said, and I'm sure it was quoted from someone else, but maybe he made it up himself. What he said is when. Again, paraphrasing. When there's no other. Let me pause this for a second. So what Sherlock Holmes, Sir Arthur Conan Doyle, via Sherlock Holmes, what he said was, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. So all right, we're not. I'd like it if we could just focus. We only got like 30 seconds left. So listen, stop putting stuff away early. I'm just going to hold you after school. 1, 2, 3, 4, 5. Everybody put their stuff away. Can stay after school today. Oh, now we stop. Now we stop moving. Why is it I have to say that? So, anyways, whatever remains, however improbable, must be the truth. So back to that alien concept, Occam's razor, right? That's just Occam's razor. You pick the simplest answer until you have evidence that says it's not. So once you start to eliminate the simpler and simpler answers, then the more complicated ones become a reality, right? So when we looked at that little light moving around, once you've eliminated gas, a kid with a flashlight, kid with a drone, once you've gone up there and started eliminating some other options, what are you left with?
Aliens.
Right? Aliens. At that point, you have to accept, no matter how improbable it is, you're looking at an alien, you have all this evidence of an alien, then you have to accept it's an alien. But it's not until then. Excuse me, I'm still trying to make a point here. It's not until then that you accept the most complicated answers. So that's why, to answer your question, which is the whole reason we started down this conversation, that's why we do chi-square analysis. That's why we don't accept this data that you see in front of you and say, okay, we're done, we did a good job, everything's right. we do an analysis, a statistical analysis. We do averages, we do means, we do standard deviations, we ask ourselves, what is this difference in mass mean? Why is there two, they're both started with 2 in this? Is this significant or is it not significant? We ask those questions of our data in order to rule out the simplest answer or collect evidence that supports the simplest answer. All right, we'll continue this tomorrow. So, okay, so now we're here with 4th period. And we have experimental group. And then we have our trial. And then we have our bag. And then we have our beaker, right? And then we have our mass. Can we close that door? And we have our aftermass. And before and after what? For those people that weren't here for the lab.
After you put it in the water.
After you leave it in the water in the beaker for a period of time, you're going to get a result. Okay. Experimental group one. Remember, was what? What was experiment? Was, okay, hypotonic meaning what? Water in the beaker. So the environment was hypotonic, so that was good. And 10% sucrose was in the bag. Okay. So who wants to be the first trial? Who wants to give us the data for their first group, first trial? Anybody have that data? All right, go ahead.
Before it was 4.4 grams, and then after we have 5.3 grams.
And the second, who wants to be the second one? Somebody? There's at least 4 or 5 groups in here. Somebody give me the data. Please make sure you don't give me the same data as another group member, don't give me the same data twice. No one else got results in this class? Not for 10% sucrose in the bag.
Ours was big. I think we did that wrong.
Just go ahead and give us a number. It doesn't matter if it's wrong. If it's wrong, this is a learning experience. So let's get the data out there.
Our before was 10.9 grams,
Uh-huh.
and our after was 20.4.
Well, you still increased
A lot.
a lot. The question, is there a question? You have a question on what, I'm going to put question because you have a question on error, right?
Mm-hmm.
You're wondering if you did an error. But I hope you're not wondering that. I hope you're not asking that question because of you're comparing your results to other people. Don't do that. Wait till the end. If yours is an outlier, then we start. Do you know what an outlier is? Okay, so if you see if your data sits on the edge of what everyone else's data is, then we start asking that question. Why? Maybe you're the only one that did it right. Right? I mean, it's possible. We don't know that. We don't know what is going on till the end. All right. Does anybody else have data? We only have 2 people with data. Is that right? We don't have time. You should have came this morning. I was here at 7:30 if you needed to come. I mean, that's okay. I'm just saying we don't have time. We have to get moving. We got it? All right, so nobody did. That's it for this class, for that data. What about trial 2? What data do we have? This is the isotonic one. Water and water. Yeah.
You want the measurements? Or?
This is team 1, or group trial 1 again. Yeah, give me the numbers.
We had 7.8 grams and then 7.8 grams.
So 7.8 and 7.8. So you actually stayed, again, very much the same. Water and water. Anybody else have water and water done?
Yes.
Trial 2 again? Yeah.
We had, for the before it was 10.4.
Uh-huh.
For the after it was 16.
So yours actually changed. This is an interesting result, isn't it? Now we're seeing some numbers that are just kind of like, okay, why? Why did 6 other groups get the same here and yours didn't get the same? So then now we're starting to think of maybe this is an experimental. Is this experimental error? Is this something that where people are making some mistakes in how to read the balance? Did people make mistakes in, was there leaking? We're not sure at this point, but this is where you start to really question the results from this trial. You see how science is working here? Okay, so this is a really good learning moment. So don't take this as being a failure. This is not a failure. The only failure in science,
Why are you looking at me?
because it's your results. I'm saying are your group's results. I don't know who else is in your group. It's not personal. I'm just saying you shouldn't look at this as a failure. You should look at this as a success because this is about learning, isn't it? All right, go ahead, next.
Ours grew 2, it was a 10.1 and then 11.3.
Okay. Next group. And this is water in water. Is that right? All right. Anybody else? Wow, nobody got any data in this class, huh? What happened? You didn't come back to check it. Yeah, that's an issue. All right, third group. All right, third group, trial 1.
I have 4.8 grams and then 4.1 grams.
So we did see a decrease, not as significant as the other classes, but there was a decrease. So that, there's always a question, is that a significant number? That's going to be something we have to discuss.
That was supposed to be a decrease for number 3?
Yes.
Oh. I think the measures are gone.
Go ahead. What did you have?
I had 8.9 and 16.9.
So now we're pretty sure, since your results are just constantly going up, right? You see that? All of yours go up. You have 16.4, you have 16.9. It seems like there's something wrong with the operators of the balance, right? This is kind of like what you're thinking when you see results like this. We're not sure yet, right? No one's making a final judgment, but that's certainly a question in our minds. 3, trial 3, what did you get?
Oh, my group measured that. I didn't get it on my chart.
Anybody else? That's a no-go, so that we only had 2 measurements on that one. Well, this was not a successful effort as the first period, but as far as collecting data, I'm sad to say. But you guys came back during lunch, didn't you?
Yeah, I didn't get it in my chart, but I believe my group did.
Well, why am I not hearing? Who else was in your group? Where are you?
Actually, for the last one, it went up too. I don't know why.
All right, so 3, yeah.
0.6 and then 4.3.
0.6, and what was the other one?
4.3.
4.3. That seems unreasonable, don't you think? Why would I say this one is really unreasonable? Because of this starting number. If all of these are starting in the range of 4s and 5s and 6, even 10s, right? In fact, somebody was wondering why one of the numbers from the last period's class was so large in the beginning. How is 0.6 a reasonable number? Doesn't seem like it is, right? So at this point, when I see numbers like that, I'm asking myself, did someone just not understand how to read the balance, right? At that point. Because that seems like, or maybe there was something wrong with because you have to get that triple beam balance, you have to get the mass in the notch. So if you don't actually get it in the notch, it could actually lead to some serious errors. So that could be a source of error, right? Yeah.
There's another kid in our group, he might have come back and measured it, but the rest of us didn't do it because there's 5 of us.
That's okay. I mean, it is what it is. This is the data we have. That's the thing about labs. You got 57 minutes. We have to do all this work. We have to collect all this data. And we sometimes have to wait and come back and get some results. And it either happens or it doesn't happen. That's what's great about collecting data like this, because now you have this data. This is first period, got it done well. And that's data you can use, right? And your data is not as useful, although trial one did an excellent job. Trial one did an excellent job. I still wonder about this, right? 0.7, but how long did you guys leave? How long did it take you? Did you leave this alone to allow this osmosis to occur? Did you leave it for 20, 40, an hour?
I set a timer for 20 minutes, but I took that one out first.
So this is probably 20 minutes, maybe less. That could explain the differences we see here, right? These guys up here, first period, I can tell you what they did is they left this alone, and then they actually came back during advisory. So a lot of these results are after about an hour and a half. Some of them came back during lunch, so over 3 hours of waiting. And like I said, 7th period, some kids came in. I'm assuming when we're done 7th period, they're going to get some fantastic results because they left it overnight. So osmosis, part of this is that you have to have time. And but what's fascinating to me, what I find exciting and interesting, is that even though you only left it for 20 minutes, right, instead of the full 40, you still got a result. Does that make sense? The gaining of mass here and gaining so much here and also gaining here puts a lot of this into question, doesn't it? It's because it's okay that it happens. If it's real, then we have to wonder, is our hypothesis correct? That is true. So we have to question what's the most likely. And that leads us into our next part of the discussion here, and that is data analysis. So we have to analyze the data. So this is data collecting. We designed the experiment, we completed the experiment, we collected the data, but now we have to analyze the data. And what are we analyzing? How significant are the results? How accurate are they? It's not a blame game. It's not, oh, you guys didn't do a good job, you guys did. That's not how you get graded for labs in this class. Do you understand that? If your information is accurate, let me say this much. In organic chemistry in college, you will be graded that way. The closer to a pure substance you get in the lab, the better your grade. So accuracy is important. But in context of this class, your grade, and obviously in research, in real research, accuracy is important. If this was experimental error, you could have, in a real laboratory, you might have wasted 3 weeks, thousands of dollars worth of reagents, a rabbit's life, right? Fish. So this could have been a lot of wasted resources. So your primary investigator, your PI, would not be very happy with you if this was a result from an error. There's never a problem as long as we fix the error and try not to let it happen again. But in a high school classroom, having this data come out this way, especially when we have a set of good data, well, I say good, I shouldn't say good or bad, a set of data that makes for a good discussion, this is fine. It does worry me we have, what is it, 2 groups that didn't give us any data at all, and one of the groups only gave us 2 of the results. That does concern me. I wonder what happened to those results. I hear you when you say you didn't have a chance to come back and weigh the second amount. But, yeah, go ahead. Yes, go ahead and use the restroom. All right, so that's the data for this experiment. Now we have to worry about analyzing it, figuring out what's important about it. Why is it that this data worked or didn't work, and what is it that it means? Because these are numbers, but there's no real meaning behind them until we analyze the data. Now, the reason I'm excited that we got the data that we did here in this period is because it lets us answer this question. This lets us use this old saying. Has anyone ever heard of Occam's razor? So Occam was a mathematician, and it's really one of his Occam's razor is really the foundation of a lot of science and math. And Occam's razor is just a principle, all right? It's from philosophy. And the way it goes is that you want to pick, and I'm going to go ahead and paraphrase, that you pick the simplest answer first before you choose the more complicated answer that gives you more, that requires more factors to align in order to get it the way you think, in order for your explanation to work. Does that make sense? So let me give you a quick example. If you see, you're at night, you're on your back porch, and you see a light moving around the sky in all kinds of weird ways, and you see it, and in that light, you see it, you hear a noise, whatever, and then you see the light moving, right? All right, some people would say a ghost right away. And some people would say alien, UFO. It is a UFO, it's an unidentified flying object, okay. But some people would say it's an alien, right? But what other possibilities might you say? Could be a science experiment, could be a kid with a flashlight playing around making noises. Okay, it could be a drone. It could be somebody with their drone flying at night, right? So there's a lot of options. So which ones are you going to pick? If you follow Occam's razor, what if it was a ghost? What would that require? That would require an entire supernatural ecosystem, right? It would require that not only that ghosts exist, but that you're able to see them and other people can't. You'd have to have an explanation of why other people can't see it. You can. Then there's a whole. So that's a ghost. Now, what if you're an alien? What would that require? That would require that there be intelligent life on another planet, and that life was able to travel to this planet, and that somehow they were really advanced and they could fly around in odd ways, but that no one else in the whole city saw it but you, and so that that requires a whole explanation there as well. And then The other explanation, I think, is probably the best one, in my opinion, and according to Occam, it would be as well. Someone with a drone. And that's a pretty easy, simple answer. So in science, you probably want to start with that one. And then you want to follow Sherlock Holmes's suggestion, right? His logic. And you'd want to say, you know Sherlock Holmes, yeah? So, have you ever heard any quotes from Sherlock Holmes? No. Yeah, what quotes have you heard?
Once you've eliminated the possible, whatever's left, no matter how improbable, is the truth.
And that's it, yeah. I think they were just impressed that she remembered the whole quote. And she said it very well. I find it difficult to remember it myself, so I'm amazed by that she remembered. But it's exactly what she says. It's listen to what she says, listen to it, and think about how logical it is, and how absolutely right. And it's based on what? On Occam's razor, right? And it's just basically, just simply, if once you've eliminated the possible, so once you say, it can't be a drone, there's no one else out there, I checked. It's not a drone. My cousin lives over there, my uncle lives here, none of us have drones, we've all gone through the woods, my dogs are out, there's no barking, for sure it was not someone with a drone. Okay, so that's been eliminated, right? So once you've eliminated the possible, then whatever's left, no matter how improbable, is the answer. So according to Occam's razor, you start with the simplest, and as you start to collect evidence that says that's not it, remember what we said in science, we don't prove anything, we do what? We disprove it. We come up with theories, and then we work with those theories until either they're proven wrong or we collect evidence that supports them. We either support them or they don't. We disprove things in science because we start with the simplest answer, we collect evidence until something tells us that it's not true, and then we go to the next most complicated one, and the next. So it could be that there's aliens out there. It's possible. It's possible that they're ghosts. But do you start with the ghost? Or do you start with the simplest answer? You hear a creak in the attic. Do you automatically assume the house is possessed and that the devil's out to get you? Well, I mean, I guess you might, but if you're doing that, it's not science, right? So science starts with the simplest answer. The house is settling. There's someone in the attic. The attic is making noises because there's mice in the walls. There's all kinds of reasons that you could say are simple. Once you've gotten rid of all those possibilities, then you can say something more supernatural or things that are more complicated are involved. So Occam's razor. Our analysis of this data has to be based on this logic. So when we look at this and we see this data that does not make sense, right? Data that's too small, data that shows increase when which should show none. Our theory says there should be none, but then we show increase. One, we need to repeat the experiments, and luckily for us, we've repeated it something like 16 times. Four times in the morning. There's a fifth time, six full sets here, including the ones from this in the first period. We have sixth period and we have seventh period. Once we've collected all that data, then we'll see. We'll be able to understand better what's going on. Ideally, what you would have loved is if the same people did all 20 trials. But that's not reasonable, right? It's not reasonable for the same 20 people. This is not a professional lab. We're not going to do the same thing 20 times, the same people in the same way. But ideally, that's what we would like to see. So now we're going to get into something called, it's 11:57 almost. So let me say this. Tomorrow we're going to get into something called chi-square. We're going to take this data and we're going to try to see what about it. Is it significant? Is this difference in this increase significant? Or could it be due to random error? we're gonna go ahead and do some analysis using chi-square. You will have to do that on your end of course exam, or I wouldn't spend our time doing it. All right, thank you for your time. Wrap your things up and have a good day. For your class, let's do the data for your class, and then, so here we are in 7th period. And let's go ahead and do an experimental group. Column. So you should have these columns, and you should have this data. That's what I expect to see when you do your write-up. What's the trial? Which trial did you do? Are we talking about? Remember, the trial is the team doing that particular trial. The bag, what was in the bag? And what was in the beaker? And then we have the mass before. Before what?
Before we put the bag in.
That's right, before we put the bag in, that's right. And then after the bag, after we put the bag in. All right, so the first group was what? The first group was the first experimental group for trial 1, that's that's whoever it is that's willing to give the data. For the bag was 10% sucrose, and then it was water in the beaker. What was somebody who wants to be trial 1, the first team to give me the information for 10% bag and beaker of water, tap water, give me the mass. Somebody have that data? Yeah, go ahead. I would just write down what I can and catch up as best you can. Next, somebody have the data for the mass before. Everybody should have mass before. Nobody has that? I'm at a loss of why some people would say to me that the person who has the data isn't here today. From the beginning of the year, I've told you that's never going to be an excuse in this class. Everybody needs to be writing down the data. Everybody knew that. You should have at least taken a picture of it. There's absolutely no excuse for this. I've told you you can have one person collect the data and submit it, but everybody has to collect the data. It's a consistent policy. This is exactly why. Honestly, I should just give you a 0 for the lab if you don't have the data. But okay, what do we have now? Somebody,
13.8.
13.8 grams? And then what's the after?
20.6.
20.6, so that shows an increase, that's fine. Anybody else? This is the only person who's gonna have data today? What did we all do all that time? What was all that running around yesterday? Wow, okay, well, that is what it is. You guys are just gonna get the grade you earned. I don't know what else to say. The second group, which is water and water, the isotonic, the same trial. What did you get for that?
28.9.
28.9,
Yes.
and then after?
28.9.
20.9. And then the third trial,
23.5.
so that's where we have 10% sucrose
Yes.
in the bag, and then we have water in the beaker. And what'd you get for that?
23.5 and it's water.
23.5, and what's this after?
10.5.
10. Wow, that's a really big difference. Did you leave it overnight or something?
We had it in there because the last period we had it in there all night. It came back this morning.
Oh, that's why. Yeah, that's the one I saw. I thought it was amazing. Thank you for correcting me. I appreciate it. It should have been water here. And 10% sucrose. Did you guys take a picture of that?
Yes.
Could you guys send me that picture of that? Because that was really beautiful. I saw it this morning. Did you throw away the bags?
Yeah, we did.
Okay, you definitely want a picture of that, because that was actually ideal. I thought it was, the reason I say it was ideal, when I looked at their bag here, this thing was swollen. Rather, I should say, this one here, it was swollen. It was really, really thick. And then this one here, it looked like it was a shriveled piece of, like, chewed up paper. And then this one here would look somewhere in between. It was just really a beautiful example of what we're talking about with this process. So even though in an experiment, we're going to go ahead and continue to experiment, any data is good data, right? I'm only celebrating the fact that it really, to me, the look of it epitomized the theory, right? But I want to emphasize that this data here is not what we expected, but that's still good data, because we can learn something from this. Any data that we can gain information on how to do something better is good information. So this is information. The bothersome thing is when there were 3 other groups in this class, 3 other trials in this class, and we have no data from it. Do you know the text of the person who has your data? The text, do you have the text that you can text them and ask them for the data? Ask them to send you a picture so you can write it down. So the data, it would have been interesting to see. It's sad that we're not going to have that possibility. But let's focus on the positive. We have a lot of trials. There's a lot of data here. We can analyze it. We can start talking about the stuff that in the video you're going to hear of me talking about a little bit out of order, because it's a discussion on Occam's razor. So I'm going to pause it here, and we'll have that discussion one-on-one. In the video, though, that discussion is already posted, or will be posted when I post this video. So what can we do with this data? What are some of the things that we can do with data that allow us to analyze it, to try to answer some, what is a basic question we're trying to answer? Yeah.
What would be the mass after we test different types of things we put around things inside the balloon?
Okay, or the bag, yeah. Yeah, that's the question we're trying to answer, right? Did the mass increase when it was supposed to increase, decrease when it was supposed to decrease, and did it stay the same when it was supposed to stay the same? If it did, then we're pretty confident that our theory is correct. So that's our objective. But the question is, how significant is this difference? Like, is 0.3, 0.6 and 4.3, could that be due to error?
Yes.
Could that be due to randomness? Could this, like we expect 23.5, we expected an increase, but is this increase significant?
Yes.
Is it significant? I don't know. I mean, 10, you say 10 is significant, maybe 10 isn't significant.
If I lose 10 inches of my height, that's pretty big.
Yeah, but if you lose 10 inches from the distance from here to the moon, that's not very big at all. So how big a difference is this, right? So that's really the question we need to answer if we're going to be able to say for definitively this is good data or this is not. Now you see how all of these have 10.5, 20.9, 20.6. You see how there's no 0 at the end? Really, we should have put a 0. It should have been 10.0, 509, and this should be 60, not 6. This is because we call this significant digits. We call this significant digits. And let's talk a little bit about what significant digits are, because that's going to be an important conversation moving forward. Whenever you have a number, let's say you have 1 here, and you all read the balance, right? And you have this little triangle that pointed to something, and you moved it, and it moved along the beam. Do you remember that? And this is 1, and this is 2, and this is 3. And in between these, 1, 2, and 3, you had these little dashes, right? So then you were able to read the ones place, that's this place, right? That's the ones place. And you're able to read then the 10th place, right? So I could put 1 if this triangle ended up being here, I could put 1.1 grams. Is that right?
Yeah.
I can write that. Now, could I guess one more? If it was in between 1 and 2, can I put 1.5? If this was pointing in between the two, can I read what's 1.5?
Yeah.
I can guess one more digit, right? I could reasonably say 1.15, right? Because it would be a guess, but I could guess it. I couldn't guess the next one. Could you guess the next one? I think it's 1.153. I can't, that's pushing it, right? So this is the significant digit. So the significant digit is the digit where you can measure plus 1, add one more digit to the right or left, right? So if I can measure to the 0.1, to the 10th place, my significant digit is going to be the 100th place because I can estimate. So I want the estimate number being part of that. So most people estimated this to be 10.50 or 90 or 60. But if we looked at first period's class data, you'll see that somebody said 2.53 or 2.55. Does that make sense? They can do that because they estimated in between these dashes. That is a significant digit, so just remember that moving forward. All right. So when you write your data from now on, you need to write down data with that significant digit, or what is it going to be if it doesn't have that significant digit? It's going to be wrong. So it's not going to be, your answer can't be 23.5. It has to be what? 23.50, 28.90, 13.80. This is important in chemistry and in college because you will literally get answers wrong if you don't put that significant digit. One number, you're guessing the number that you can actually read, plus one digit for guessing. Now you're going to watch a video until the end of the period because it looks like we're going to have just enough time to watch it. It's on chi-square. That's going to answer the question, is the difference between what you expected and what you got, is that difference significant? Or is it due to random chance? This is just an introduction. Tomorrow we'll get into some practice calculations. All right, I'm going to pause it here, and I'll try to add the video to this video.